Hey everyone, my name is Venelin, and in today's video I'm going to show you how you can use sentence transformers in order to find how similar two or more sentences are. I'm going to show you what sentence transformers are, what Siamese networks are and how they relate, and then we are going to briefly have a look at MPNet, which is a Microsoft network that is using a very different way to train BERT-like models or transformers. We are going to combine everything into one or more simple examples in which I'm going to show you how you can use semantic similarity search and how you can score how similar two sentences or more sentences are. And at the end, I'm going to show you how you can fine-tune the existing models on your examples and get better results on your task. Let's get started. We're trying to find how similar two sentences are. So for example, we have these two sentences. Bitcoin is up 34% since Bank of England governor said be prepared to lose your money in BTC and crypto. And then the second sentence is one of the biggest bull traps I've ever seen. So how similar are these and how we can find this similarity? So to solve this question, we are going to use a library called sentence transformers, and this is the website of it. It says that it is a Python framework for state-of-the-art sentence, text, and image embeddings. And there is a paper that is linked right here, which states that the initial work was done over there. And if you go to the paper, it is from 2019. This paper, it's called SBERT, Sentence Embedding Using Siamese BERT Networks. So this is pretty interesting work, and it talks about, at least in the abstract, about the fact that the original BERT and RBERT are very good models and they provide state-of-the-art performance on sentence per regression task, like things like semantic textual similarity. So this is what we are trying to solve here. Essentially, what this does is to compare a pair of sentences and tell us how similar they are, and if there are the maximum score that you can get is 1, and if they are maximally dissimilar, the score is minus 0.1, and of course neutral score gives you 0. So in order to solve this task, there is this, you can use BERT, but it appears that BERT or similar models are very slow, and it takes a lot of time to do this search or semantic similarity scoring. Another approach that they tried out is using these Siamese neural networks, and they essentially modified BERT in order to speed up drastically the performance of those pairing and scoring. And it says that when they implemented this model, it went from 65 hours to 5 seconds. So this is a very, very substantial speed up. And essentially what those guys did is to create this library, which is available now, and you can use it with Python, and it is written in PyTorch. The good thing is that it has very nicely integrated with transformers as well, and it allows you to use a lot of pre-trained models, as you can see here, and the authors of the library have created this very nice leaderboard, and they gave you a relative performance of each of the models. Today we're going to use the first one, but I'm going to go over that in a bit. And as you can see, we have a very nice documentation right here. Of course, the library is open source, and it is available on GitHub if you want to have a look at it. So if you don't know what these Siamese networks are, there is a very good example in the PyTorch examples. It is in the PyTorch examples repo, and there is Siamese network and then a main script. And in this example, the script or the example is using image similarity as the task that is given right here. So what those type of Siamese networks are doing is essentially using the same network for two different inputs and then comparing the results as a scoring function. I'm going to show you the training. I think that there was, yeah, here it is. So what essentially the sentence transformers are doing is reusing the same neural network, and they're passing two different sentences through it, and then using a classifier on top of it to say whether or not or how similar -1 to 1 those two sentences are. So this is what is done essentially here in this Siamese network example as well. And the most important part, at least for me, while looking through the code, is this method called forward once, which is essentially the forward method that you find in pretty much any neural network that you're writing. Some details here, they're using ResNet, etc. as an architecture, but that's not really important. But the most important part right here is that in this forward method, instead of accepting a single tensor for the data, you're actually accepting two inputs. And as you can see, both of the inputs are passed through the network. And then once this is done, this is passed through a sigmoid layer or a function, activation function, and then the result is given. So this is essentially the similarity score. And if you go a bit down, you see that they're also creating this dataset, which essentially is doing the following. This is working on the MNIST. So if you're familiar with the MNIST, it's a dataset of handwritten digits. So you have 0 to 9. And essentially what they are doing is picking some image, and on this image they know the digit on it, and once they know the digit, they can for example take another image of the same digit and say that this is the same digit, so that the label for it will be 1 or a positive label. Otherwise, they can take any digit that is different from the current one and take a random image from it, and then they say that this is a negative example or 0, so there are dissimilar. So in this way, you can essentially train similar and dissimilar images. So it works pretty well, and that's pretty much how at least basic Siamese networks work. So it's very straightforward, and I would say very intuitive way to train those type of networks. So let's start with the notebook. And these are the sentences that we were interested in initially. So the first thing that I'm going to do is install the sentence transformers library. So as you can see, I'm just in case upgrading pip, and this is the latest version of sentence transformers 2.2.2. There is ongoing development at least at the current time, and there might be newer versions that are just around the block, if you will. But at least for now, I'm going to stay with the latest production version. Then I'm going to import the model or the model placeholder, and then the util library from it. And this should run through importing these. Maybe I need to restart the runtime. So maybe I have a typo. Yeah. All right. So once this is imported, I can create a model here. And for the model, I'm going to use this leaderboard, and essentially I'm going to take the best or the best performing model, which is this model MP-net base, which is a model that is trained by Microsoft, which is the initial version of it. And it's, let's say, a different way to train BERT or BERT-like models. And there is a paper and a GitHub repo of it. It's called MP-net, and it's open source on GitHub thanks to Microsoft. So essentially, those guys are also, they're also have the paper here, and they're focusing essentially on a newer way to train BERT-like models. And here they're representing this mix of masked language modeling and permuted language modeling. So there are working, there is an explanation on papers with code, and it says that it's a newer method of training which combines both masked language modeling and permuted language modeling. And there is a bit more of details here how this model is trained. I'm not going to focus a lot of it on it a lot, and you can read through the paper if you will. But at least from the objectives and the results of the paper, you can see some very good improvements compared to the BERT and other models on various tasks. And this is essentially the base model that is trained using the sentence transformers. And it says that it's been trained on a large and diverse data set of over 1 billion training pairs or sentences. So here you have max sequence length, which we are going to check, and then the dimensions, which are essentially equal to what you get from BERT base. Some of the more popular models are something like this, Mini LM, which of course also is based on a Microsoft model. This one is also very popular. But I would say the most powerful one is this one, and we are going to use it in this tutorial. Of course, you can try out any of the others if you want to. So to use this, I'm going to specify sentence transformers, MP-net base v2. So this will go and download the model for us. And there is also a model card right here on the Hugging Face Hub. So you can have a deeper look at what the model is doing. There is also this playground, if you will, where you can try it out. And once this model is downloaded and loaded, I can check the max sequence length. And this should max sequence length, yes, 384. So this is the maximum number of characters or tokens that your model can take. So next I'm going to create or get a corpus of different sentences, two of which we've already seen. And this is our corpus of different sentences. So the task here would be to use this corpus in order to create embeddings using our models. So the model is going to essentially compute this vector of 768 for each sentence, and then we can use cosine similarity in order to get how similar to a pair or two sentences are. So to compute this embedding, I'm going to use the model. I'm going to show the progress bar. It's going to be quick, but that's all right. And I want to convert the result to a tensor. Yeah, pretty fast, even though we are running on a CPU. And what does this have? We have, I believe, 10 different, 10 different sentences in our corpus. And since we wanted this to return a tensor, you're given a tensor of 10 with 768. So for essentially for each sentence, we have this vector, which is the embedding vector given by this pre-trained model, and how we can use this in order to compare the similarity to something. Well, first I'm going to create a query, which is essentially going to be a question, or and I would like to know how similar each of those sentences are to this query, but I can't pass it in just like that. I also need to create an embedding for it. And I want to convert this to a tensor as well. So now that we have the embedding of the query, which is again this vector, we have pretty much everything that we want. And then I'm going to use the cosine similarity from the utils of the library. And let's ask this versus, for example, the first one. So we have pretty high score, and this is Bitcoin is up, etc. Let's say that I have, as you can see, I have a mix of crypto tweets, and then I have some tweets for powerlifting, weightlifting, etc. So the first one is very similar to Bitcoin, and let's say the last one is fairly dissimilar. So this is all about powerlifting. So it says that it's very dissimilar, which is good. And how our two sentences are doing? Let's check them out. So if I do the embedding of the first sentence, and I do the embedding of the second sentence, and I compare their similarity, as you can see, not that similar, at least according to this model. Even though I would say that they are very similar in their sentiment, but not in their wording, if you will. So this is a bit more deeper than the model can understand. Okay, so we have this, but we were trying to do this query thing. And as you can see, you can calculate the similarity for a specific sentence. And one thing that you might want to do is that given a query, you would like to do a search of how similar something is. So one thing that you might want to do is to compute the similarity for each embedding and then maybe sort it. But luckily for us, there is also already this functionality included into the sentences transformer library. It's called semantic search. And here I'm going to pass in the query embedding and the corpus embeddings. And let's have a look at the result. As you can see, it's a list of lists, and I'm going to take out the outer list from it. And as you can see, you're given a score, and then you are given the corpus ID, as you can see here. So you might note that this is not sorted according to the initial order, but it is sorted according to the score here. So the thing that I'm going to do here is to use each item in this and print the score. And then look through the corpus. Print it out. So how high will Bitcoin go? As you can see, the first thing is how I sleep knowing Ethereum is going to 10K in 2023. So this is the most similar. And then Bitcoin is up. This is the second. Then is the BTC bottom in. All right, so this is the new sorting, at least according to those scores. Let's try another query. Let's try how much should I deadlift at 82 kg body weight. Let's see for this one. If I go through this, and then the sorting is completely different. The sport of powerlifting includes squat, bench, and deadlift, but the concept of powerlifting is force equals mass times acceleration. And then more about powerlifting. I would say that this is doing a very good job. It is putting everything that is about Bitcoin or cryptocurrency at the bottom, and then everything about powerlifting at the top. So it works quite well, I would say. And let's have a look at how you can train your own model. So if you don't like the initial scoring, we were talking about this here with the Bitcoin. And I would like to include or import from the sentence transformers the dataset, the input example, and the losses. And I'm going to show you how we are going to use this. So first, I'm going to create a dataset with this sentences dataset. And in here, I'm going to create a single example. And this is the input example. And this accepts texts and then a label. And the label I would like to be 0.9. And I'm going to input those two sentences since we started with these. So the dataset also wants a reference to the model. So I'm going to pass it in. Good. Now I'm going to create a basic data loader using the PyTorch data loader. And I want it to be shuffled. And then I'm going to create a loss function, which is using, again, the library, which is going to be using cosine similarity loss. And this should take the model. And finally, I'm going to pass in a safe path where the trained model is going to be passed in. So now that I have all the components, I can start with the training, and this is pretty easy. I'm going to call model.fit, and this accepts train objectives, which are going to be the data water and the loss. I'm going to train this for 10 epochs. I'm going to pass in warm-up steps equal to 10. You don't need to, but I'm just showing you how you can do it. And then the output path, which is going to be the safe path. And this should start the training. It should be pretty fast since we're working with a single example from here. And I'm going to go and create these or copy these since we're going to try out the new model right here. But I'm going to call this trained model. And to load the model itself, I'm going to pass in the safe path. So safe underscore path. And this should recalculate the embeddings. And I'm going to paste in the similarity computation. You've seen that 0.14 was before training the model. And now that this is trained, let's see what is the score right now. And it says 0.9, which is very similar to the label that we have here. So it appears that the training is doing something. Of course, you would want to have a lot more examples in order to train your models. So this is pretty much it. You can use sentence transformers for similarity scoring, and you can use it for semantic search. You can also use them for image similarity search, which is another very good way to use those types of models. Thanks for watching, guys. Please like, share, and subscribe, and I'll see you in the next one. Bye.